Alrighty, AP Chemistry students, here is Set 2. Now, Set 2, believe it or not, is mostly a lot of review. Okay, a lot of review of the atomic structure. A couple of things at the end will be new to you and something that we have to know for AP. But let's start off simple. Let's start off with a simple structure of the atom. You guys should know by now that the nucleus of the atom is made of protons and neutrons. Alright? And I've illustrated them in the center there. The red dots are the protons. Those are your positively charged subatomic particles. Then you have your neutrons in blue, which are a subatomic particle that does not have a charge. Okay, it's simply there for stability purposes. And then zooming around the outside of the atom, you have the electron, which is in an electron cloud. Remember, the electrons are negatively charged and they essentially have no mass. Okay, they are very, very small, and you'll find out why they essentially have no mass a little bit later on. Let's move on to the next portion, and that is the nucleus of the atom. The nucleus of the atom is very, very important. Okay, the nucleus is made up of protons and neutrons. The number of protons determines the identity of the element. Alright? So if you have one proton, you are hydrogen. If you add another proton onto it, you become helium. 3 protons is lithium, 4 protons is beryllium, so forth and so on. Okay? So if you change the number of protons, you change the identity of the element. Okay? Protons and neutrons together make up the atomic mass of the element, so how heavy that element is. Let's take, for example, the sample that we had above, up here. There were 2 protons and 2 neutrons together. If we add those up, we would get a total of 4 atomic mass units. Okay, I forgot to put mass in between, so I added the caret there. 2 protons plus 2 neutrons is 4 atomic mass units. Okay. This element is obviously helium because it has 2 protons. Now, the atomic number of the element, ladies and gents, is the number of protons that it has, and we will go into a little bit more detail about that when we get to set 3 or 4, which is the periodic table. But if you look at a periodic table and you look at the top number above the element symbol, that is the atomic number. Okay, that number tells you the number of protons an element has. Okay, so all you would have to do to figure out the neutrons is subtract that from the mass, and we'll go into that right now when we talk about isotopes. Okay, now isotopes are kind of a review. Kind of not, because we didn't go into them in great detail in regular chemistry or CP or scholars chemistry. So let's just talk a little bit about what a isotope is. An isotope is an element of the same type, but they have different numbers of neutrons. Okay, so element of the same type, meaning if we're going to have isotopes of, in this case, hydrogen, they will always be hydrogen, but they will have a different number of neutrons. Okay, you're allowed to do that. So let's take regular old hydrogen, the hydrogen that we know that occurs, I should say, mostly in the environment, the most abundant form. Hydrogen traditionally has a mass of 1, and this top number right here represents the mass. It always has an atomic number of 1. That will never change for hydrogen. Atomic number, or the number of protons, is always 1. That's represented by this bottom number right here. If you subtract the mass and the atomic number, you will get the number of neutrons. Okay? So hydrogen, as it normally exists, does not have any neutrons. Okay? It is stable without a neutron. Let's say we went ahead and gave hydrogen a neutron. What would its mass be then? If you said 2, you were correct. Okay? This is deuterium, ladies and gents. Deuterium is hydrogen that has a mass of 2 and an atomic number of 1. Notice how the atomic number did not change. Okay? The atomic number being the number of protons. That never changes for an element, because if you change the protons, you change the element itself. And we're not changing elements, it's still hydrogen. Alright? Mass of 2, atomic number of 1. If we subtract those two, deuterium has 1 neutron. 1 neutron. So as you can see, they're both hydrogen, it's just one of them has a neutron added to it. Okay? This element is obviously a little bit heavier, and it's used a lot in industry, especially in nuclear reactors, when we want to slow down nuclear reactions. Now let's look at tritium. Okay? Tritium has a mass of 3 and an atomic number of 1. 1 proton, okay, because it's still hydrogen. That does not change, but its mass can change. If we have a mass of 3, an atomic number of 1, we can subtract those two, and we figure out that it has 2 neutrons. Okay? It's still hydrogen, just hydrogen with 2 neutrons added to it. And I went ahead and put the radiation symbol next to it just for fun, because tritium is a very radioactive element. In fact, we use it in nuclear bombs, hydrogen bombs more specifically. So just as a review, isotopes, they are the same element, but they have different numbers of neutrons. Okay? Their atomic symbols stay the same, and their atomic numbers stay the same, but their masses will change as well as the number of neutrons. Okay? And this can happen for any element on the periodic table. Happens a lot with hydrogen, also happens quite a bit with carbon, when we're looking at carbon dating certain things. Iodine and cesium will have different isotopes as well, especially in nuclear reactors. Okay? Radioactive. Alright, let's move on to the next portion. And that is the energy level in an atom, ladies and gents. Now this is a review. We've done energy levels before. Energy levels describe the amount of energy an electron has in an atom. Further away from the nucleus an electron is, the more energy it has. Okay? Now the reason why that occurs is because the nucleus overall has a positive charge. Okay? The neutrons don't affect the charge at all. There's only positively charged particles in the nucleus. Okay? So if the nucleus is positive, the electron is negative. Okay? Sorry. And you guys know that opposites attract. Okay? So electrons are attracted to the nucleus. The closer it is to the nucleus, the happier it is. If you move it further away from the nucleus, it's going to have more energy. It does not like being far away from the nucleus because it's negatively charged. It wants to be very close to that positive nucleus. Alrighty? So electrons have more energy the further away they are, and less energy the closer they are to the nucleus. That's why they're called higher energy levels when you go further out. You can move an electron from one of the lower energy levels to the higher energy levels, like setting it on fire or zapping it with electricity. If you recall the flame test lab that we did at the beginning of the year when you took chemistry, we put those different solids in the flame and it gave off a special color. That's because you were moving the electrons to a different energy level, and when the electrons jumped back down, it gave off that color of light. We will see that happen too. I am going to show you guys what jumping electrons actually look like about the first, second or third week of school, depending on if we can get that supplies in time. It might not happen second or third week, but it will happen for sure. We will see electrons jumping. Okay. Now, this was a very nice, introductory model of the atom. The atom is actually very, very, very complicated. It's way more complicated than just these energy levels hanging around it. That is because the electron itself is very complicated. We think of electrons as these tiny little particles that are just zooming around the atom, and that just simply isn't the case. All right? The electron has the properties of both a particle and a wave. Now, for those of you that have already taken physics, you know what waves are. Okay? How can something have the properties of both a wave and a particle at the same time? Okay? Because waves move differently through space than electrons or than particles do. Well, that's what quantum mechanics is. Now, you don't need to know this in great detail. You just need to know that the electron has both of these properties, and we call this a wave-particle duality. A wave-particle duality. It's not necessary to know this for the AP exam. It's just something that you should have in the back of your head. Okay? And so what an electron, this isn't a very good drawing, but what an electron cloud really should look like if we did the Bohr model of it is you would see these different waves as energy levels, these standing waves. The higher the energy the electron has, the crazier the shape of the wave gets. And we're going to look at a few of the shapes of those waves, okay? Now, we can never exactly pinpoint the exact position of electron in an atom. We can only take a guess using very complicated math, but it's a pretty good guess because we can get it with 90% accuracy. All right? So what that means is we can never pinpoint the exact location of an electron in an atom, but we can get a good guess with 90% accuracy where it is. The area where you are 90% likely to find the electron is called the orbital. The orbital. 90% likely to find an electron in that area. And these orbitals have different shapes, and those shapes are the wave functions. What do those wave functions look like? Here are the shapes of the different orbitals, ladies and gents, and they increase in energy as we go across. The simplest orbital is the s orbital. It's just a sphere. Okay. Now this sphere is an imaginary region where you are 90% likely to find an electron that's closest to the nucleus. If we get a little higher in energy, we will have what's known as the p orbital. And the p orbitals, there are 3 of them. Okay, there's one p orbital oriented on the y-axis, one p orbital oriented along the x-axis, and then one p orbital oriented along the z-axis. Okay. These orbitals will overlap each other. I just separated them out so you can see the 3 different types, but when they overlap, they form the sublevel. Okay, they form the sublevel. Let's get a little higher in energy, and then we'll have the d orbital. Now, this is where the shapes start getting very, very crazy, and I only drew one of the shapes for the d orbital. There are 5 total, but the other shapes are a little bit more complicated, and I decided not to draw them because it gets really hard. Let's go up a little higher in energy and you'll have the f orbital. Alright? There are 7 total f orbitals in that sublevel, and I only drew the easiest one. Okay? As you can see, the shapes of these waves, these are waves right here, they get more complicated the more energy the electron has. Okay? And as you get to higher level atoms, you have to fill higher energy levels. If you recall from regular chemistry, we would fill up one ring, then we would go to the next ring, we would fill that one up, then we would go to the next one, fill that one up, go to the next one, so forth and so on. And so as we get to these higher rings, or waves I should say, their shapes get more complicated. Now each orbital can occupy no more than 2 electrons at one time. Okay? That's called the Pauli exclusion principle right there. Alright, ladies and gents, this was just a brief crash course into what the orbital is. This stuff right here is new stuff, but everything else that came before it is review. We'll see you back for set 3. Go ahead and take care and go ahead and do those practice problems to the best of your ability, and we'll see you next time.